Hello everyone and welcome to ME304 Machine Analysis and Design. This is a problem we're going to be doing. We have a shaft that's undergoing cyclical torsion, so it's being jerked back and forth like this with the tension force of 80, or the torsion force of plus or minus 80 newtons per meter. Go ahead and pause the video right here and write down this problem if you want to. I'm just going to go ahead and go straight into the solution. Alright, so with torsional loading, normally what you have to do in order to do the cyclical stress is use the modified Goodman method. So that's what we're going to do. Modified Goodman method. And what it gives you is a sigma prime A plus sigma m A all over the ultimate strength, all over the strength endurance, or the endurance strength, however your professors define this for you, is equal to 1 over factor safety. Now, we can get this value from the endurance equation, the endurance limit method, sorry. This is from the charts. These are also from the endurance limit method, and a few extra stress equations. And then, of course, this is given to us in the problem. So, I'm going to start out trying to find SE. So, to find SE, you have to use the equation SE is equal to KA times KB times KC times times KD times KE times KF times SE prime. So what are all these values? Well, they're all values that you can get from the tables within the book. In my course, we use Shigley Mechanical Analysis and Design. So we'll start with KA, since it's the first one. These are all endurance factors that you get from the tables based on like temperature or weight or stress or ambient conditions or something. So these are basically conditions within the shaft that reduce its ability to withstand loads. So KA is equal to ASUTB. And in the Shigley book, it's table 6.2, where you get these values from. Now, SUT, of course, you look up in the back of the book for the material that we're using. In this case, it's the type of steel. Or you might have to use Mill Handbook 5. I'm not sure. No, you can use the back of the book for this one. And then A and B are based on the type of metal that you have. Like, is it ground, or is it milled, or so on and so forth. And that's how you get these. So these are basically surface conditions that affect the strength. So you solve that, you get Ka. And if you actually solve this here, A will equal 57.7. And of course, S ultimate is 520 megapascals, all to the power of negative 0.718. Okay, and if you solve that out, you end up with 0.647. Okay, so that's our Ka. Now we go on to Kb, which is another equation. It's the size factor, and it's dependent on how big the shaft is relative to the other shaft, and so on and so forth. If you look at the tables, you'll see how this is obtained. So it is equal to 1.24 d to the negative 0.107, because d is less than 51 millimeters, which is the size of our shaft. And if you do this, you can go ahead and you'll find out it's 1.24 times 25 millimeters to the negative 0.107. And that will all equal 0.879. So both of these you get from tables. All the values come from tables based on the conditions of the problem. Then you come on to Kc, again another table which is dependent on the type of loading. And since it's a torsion loading, it's going to give us 0.59. Then right off the top of my head, I don't remember the other ones, but based on bending or axial loading, this goes up and down to like 0.95 and like might be 0.75. I don't remember what those two other values are. But again, look this up in the book for KC. The chapter should give you all the tables that you need for this. And then KD, KE, and KF, they are all, this one's for temperature. This one is a second kind of a side. This is, well, no. Let me complete that thought. This one is miscellaneous. And this one is based on survivability or reliability. I'm sorry. So if you want like a 99% reliability or something like that based on a certain loading, you get KE. But in most reliability, in most cases, it's just going to equal 1. So all of these are just going to equal 1. So that's how you get that. So then if you're solving for SE, you're going to end up, oh, I forgot one other thing. SE prime. SE prime is actually pretty darn easy because it is equal to 0.5 SUT, which in this case, when you do that math, is 26 megapascals, or 260 megapascals. Now, this 0.5, this is not universal. This SE is not universal for all sizes, but usually in most problems, you're going to be dealing with shafts that are fairly small, like under half a foot or something like that. But as you get into larger shafts, this SE changes and this coefficient changes right here. So again, look at your book, make sure you know what your problem is. But in this case, with this small of a shaft, the equation that we use is right, this one right here. So now we can solve for SE, which is then equal to 0.647 times 0.879 times 0.59 times 260 megapascals. And you end up with your endurance limit, or endurance strength, being 87.2 megapascals. So, within the fatigue and the stress that you're putting on this, the amount of fatigue that you're putting on this is going to max out at 87.2. So now, what we have to do is define, to continue on and get the sigma A prime and sigma M prime, we got SE. But to get those other two, we actually have to define normal stresses. And we're going to start out with tau xy. And it is equal to KTS, because we have a stress concentration. This is a stress concentration coefficient. 16T all over pi d cubed. And again, tables. You go back into your stress concentration charts for a shaft with a fillet around it. You'll find KTS based off of D over D and R over D. And these are both equal to 1.2, and this one's equal to 0.1 in this case. So you use these, you look at the chart in the back of the book, you line these two up as the 2 points on that chart, and you get your KTS. You put it into here, we have our torque, and we'll go ahead and solve this. So you'll find out that KTS is equal to 1.35 times 16 times 80 newtons per meter, which is the maximum load that you'll feel. This is the maximum torsion that you'll feel in any direction. Certainly, if you're looking at how the loading is going, since it's plus or minus 80, it's following a sine wave like this. But the most you ever feel is a magnitude of 80 newtons per meter. So that's what you'd use for this equation. That's pi over 0.025 meters cubed. And that's going to equal 35.2 megapascals. Okay, so we got tau xy. One note about this. This equation is used for cyclical loading if you are, oh, excuse me. Let me make sure I'm not telling a lie here. No, I take that back. This equation is just fine the way it is. Go ahead and find the stress. In the next equations that we do, we're going to change it up a little bit. Now, pure torsion. Yeah, I can't draw right or spell. Pure torsion. The only thing occurring on the shaft is torsion. It's only being twisted back and forth like this. It's not being bent. It's not being jerked on. It's just being twisted. So you can consider this a pure torsion system. So because of that, sigma A is going to equal 0. And This is standard for no matter whatever happens, pure torsion, so on and so forth. Sigma A is equal to 0, so then tau A is going to equal something. We'll get to that in a second. I want to talk about pure bending just very quickly. In a pure bending situation, where all you're doing is bending on a shaft or something, and you're not pulling or twisting at all. In a pure bending situation, let me check my notes, make sure I don't tell you a lie because I don't want to confuse you. Then, hang on. Sigma A due to rotation. Sigma M is equal to 0 in this case. In a steady torsion, you have a constant TA, and alternate. Okay, yes, there we go. So, if you're not familiar with sigma M, it'll become clear in a second. But in pure bending, sigma M is 0, and in pure torsion, sigma A is 0. And the tau, you'll always have a tau A, no matter what. And then you'll also have a tau mean, because as a bar spins, if you can imagine it, if I put a little bit of bend on this bar in a pure bending situation, and I start spinning it, it doesn't really have any torsion stresses on it because the entire bar is spinning. But if you bend it just a little bit and then spin it around, the top part will feel an axial stress, a positive axial stress, and the bottom part will feel a compressive axial stress at these little local locations right here at the tip if I bend it like this. And as you spin it around, you can see how that will alternate from one side of the pin to the other as I do this. So that's why the pure bending is like that, because the sigma mean, the stress, the average stress as you're going around in a circle is 0, because since it's cyclical, again the sine wave, if you take the average of the sine wave, it's just 0. So that's what the sigma mean is, because this is sigma, the graph of sigma, and sigma mean is equal to 0. The same kind of thing is occurring over here with sigma A, but, well, there's no, it's not the same thing. Sigma A is 0 because in this case, with torsion, you don't have any axial or bending stresses anywhere. So the axial stress is just 0 because there's nothing being pulled or pushed anywhere. Okay, so then moving on with that, tau A, the shear stress, the actual shear stress, is changing because you're jerking it back and forth like this. So there's a lot of shear going on. So in order to find that out, you take your stress, your shear stress up here, which you calculated based on the axial loading. So it will be going back and forth between 35.2 and negative 35.2, because this is actually plus or minus up here, but we did it as a magnitude, so this will be plus or minus down here. So what you have to do is you need to take those two extremes, draw the sine wave again, just because it's what's going on. You've got this load, and the shear is in between there, so you can basically take the magnitude of the peak to peak here. So in order, the average of those two peak to peak. And you might not always have a perfectly symmetrical sine wave around the axis. It could be adjusted up here a little bit, something like that. So you have to take the average in order to get what the value of the adjacent or shear stress is. So this is going to be 35.2 minus the bottom. So this is 35.2. This is negative 35.2. So minus negative 35.2 and divide it by 2 to split this in half and get the magnitude of it. And if you do that, you'll end up with 35.2, oddly enough. I remember this pure bending is just for a different situation. I just showed it to you to kind of give you an introduction to that. This is a pure torsion situation, so this is what you're using. Okay, and then sigma mean, the average sigma, well, it's equal to 0, so the average sigma is equal to 0 because any kind of sigma is equal to 0. And then the tau mean, well, right here, if you take the average of this, you go ahead and you get 0. This was not the average, this was the half magnitude of it. So you can figure out what the maximum is. I was calling that average, this is not the average. An average would be an addition. But with this one, the average is 0, because if you take the average of the sine wave, you get the center axis, and in this case it's 0, because it's symmetric around that axis. Okay, so that was a bunch of talking and not very much math, but hopefully you understand it a little bit better now. So now that we have all these values going through here, you should have been introduced to the equation of sigma prime is equal to sigma sigma A or M is equal to sigma A or M squared. Now these are just to define different equations. This is sigma A squared, or in order to solve for sigma M, you use sigma M squared over here. Real prime. And then plus 3 tau A or M, depending on which equation you're working with, squared to the 1/2. Okay, so then solving these out, if we're going for sigma A prime, that's going to equal sigma A squared plus 3 tau A squared to the 1/2. Well, sigma A is equal to 0. So we've got, this is all equal to the square root 3 of tau A, because you got this square root of a square right here, and the square root of 3 right there. Tau A, which is then equal to this value up here, square root of 3 times 35.2, and that is going to equal 61.0 megapascals. There we go. So we got sigma A prime, and then sigma M prime is going to equal 0, because both of these values are equal to 0, so when you put them in here, they both equal 0. Okay, cool. So we're on the home stretch now. We can go back and do our modified Goodman equation right here. We've got sigma A, sigma prime. So we've got sigma A prime all over SE plus 0, because sigma M is equal to 0. Sigma M prime is equal to 0. Is equal to 1 over N. So we go to 61 megapascals all over 87.2 megapascals is equal to 1 over N. So now solving for the factor of safety that we're going after is equal to 1.43. Okay, so that's our N for this situation that we've been given. And now we need to figure out what our margin of safety is to see if, well, is this factor of safety good enough for this situation to make sure that the system doesn't fail. So the margin of safety is equal to 1.43, the value we got, over the value we want, minus 1, which is equal to negative 0.046. We have a negative value in the margin of safety, means it fails. So in the situation we've been given, there's no way the shaft will be appropriately strong with this margin of safety in order to meet the standard that we're setting of 0 or 1.5. So this is not a good enough system. This doesn't mean that the system fails particularly, but it does mean that it fails the criteria. So don't be confused by fails. It doesn't mean everything breaks, but it means that it doesn't hit the standard that we want. So that's how you go about that. And you can pretty much tell that because our margin of safety was smaller than this margin of safety. So, oh, well, it's not the one we wanted. And that is how you use modified Goodman in a cyclical torsion shaft analysis.